Today we're going to finish up on volume, and today's volume problems are going to be within problems that we know what the cross-section is going to look like. Remember, if we cut a figure in half and looked at just what figure is looking at us, that's called the cross-section. Well, how do we find the volume of that? Well, if we know that all the cross-sections are the same, then we can take the area of each of those, add them all up, and that'll give us the volume. Well, how do I add all those up? I integrate. So I'm going to integrate from A to B of the area of each of those figures. So A of x is going to be the area of each of the cross sections. So let's go ahead and look at an example 1, where we're going to find the volume of a solid whose base is bound by the graphs of y equals the square root of 9 minus x squared and y equals 0. I'm going to go ahead and stop right there so we can draw out this picture of what exactly we're looking at. So we're going to take y equals the square root of 9 minus x squared. And that's going to look something like this, where we're going to come out here to here and up to this point here. I can throw this into the calculator. I know that I'm going to come out to -3, and I'm coming out here to 3, and I'm coming up to a height of 3. Some of those may be important as we get into it, others may not. And then y equals 0 is going to be the x-axis, whose cross-sections are then taken perpendicular to the x-axis. So we know that we're going perpendicular to the x-axis, so we're going up and down to create our figure. So maybe if we draw in a few of those lines, that's kind of going to be what we look for. So what do we know that those cross sections are? Well, in part A here, it's telling us that they're squares. What do I know about a square? A square is equal on all of our sides. And to find the area of a square, I take my length and I square it, or my sides squared. So what I'm going to do is I'm going to create squares on this figure all the way across. So if I come up this distance, I'm also coming out this distance. So I'm going to create a bunch of squares on this figure. So kind of think of it as a three-dimensional, and I've got a bunch of squares added up. They're going to start very small, and as I work up, it's going to come up and it's going to go back down. Kind of what we saw in that animation, if you want to go back and look at a couple of those animations. So how do I find the volume of this? Well, I've got to add all these squares up, or the area of each of those squares. So I'm going to have the integration from -3 to 3. So that's to my endpoints. How do I find the area of a square? I take the side length and I square it. Well, my side length in this case is going to be the distance from the x-axis up to the curve. And the value of that curve is going to be given to us as the square root of 9 minus x squared. I'm going to multiply it to itself, or square it, since that's the area of a square. If you think about the area of a square, area equals side squared. My side in this case is my function, so my area is f of x squared, and f of x in this case is the square root of 9 minus x squared. I'm in my variable of x, so I can go and integrate this part. So I can integrate from -3 to 3 of 9 minus x squared dx. Now again, we could see that this is an even function, hopefully. And since that's an even function, we could take this as the volume of 2 integrations from 0 to 3 of 9 minus x squared dx. But again, since we have a calculator, it's not going to matter a whole lot which one of those we do. So in this case, we're going to go and integrate our math 9 from -3 to 3 of 9 minus x squared dx. Go and get that calculation, and we end up with a nice clean answer of 36. Notice we don't have a pi in our volume with this one. We don't need the pi in there because we're not working with circles. Yes, we have this radical here that looks circular, but each of these cross sections is just a square, and we don't have pi within a cross section of a square for the area. Now, we are going to see this later on come into play. So in example B, we're going to find that we have rectangles with height 5. Again, I want to use that same figure, but now, instead of a square, we're going to put rectangles on each of these lines. So how do I find the area of a rectangle? Again, I'm going to take the area from A to B for my volume, and I'm going to find the area of a rectangle. Area of a rectangle is going to be length times the width, dx. Well, in this case, instead of a width, I have a height, or we can talk about it as length, doesn't matter. So we have the integration. Again, we're going from -3 to 3. Our length or width is 5 times, well, what is the other dimension? The other dimension is going to be the distance that we have from the x-axis up to the function, or f of x. In this case, our f of x was the square root of 9 minus x squared dx. Again, this is definitely going to be a calculator question, since we can't integrate easily the square root of 9 minus x squared. So I'm going to go math 9, -3 to 3 of 5 square roots of 9 minus x squared dx. Go and allow it to work for a few minutes, seconds probably more than minutes. We wait patiently waiting. We get it. We end up with 70.6858, which is 70.686 as our rounded answer. Semicircles, we're going to again use the same figure there. Little more complicated when we talk about semicircles, because now what's going to happen is we need the area of a semicircle. Remember, the area of a semicircle is 1/2 pi r squared dx from A to B. Is going to be our volume. Well, we know our A and our B is -3 to 3. Our 1/2 pi, that's not a big deal. That comes out to the front. So we have 1/2 pi integration from -3 to 3 of our radius. Well, what is our radius now? If I create a semicircle there on top of each of these, then I need to know what the radius is. The radius is going to be half of the distance from the x-axis up to that graph. So what I've got to do is take half of f of x. So I take the square root of 9 minus x squared, and I'm going to divide it by 2 and square it, dx. So now I have the volume as being 1/2 pi times the integration from -3 to 3 of the square root of 9 minus x squared divided by 2 squared dx, because this now is my radius. So that's going to look like 1/2 pi, integration from -3 to 3. If I square this out, it actually becomes a little nicer, because I get 9 minus x squared over 4 dx. I could bring that 4 out. So I get 1/8 pi, integration from -3 to 3 of 9 minus x squared dx. Well, now if I go ahead and throw that into the calculator, I have 1 divided by 8 pi, and then times the integration, math 9, from -3 to 3 of 9 minus x squared dx. Allow it to think there for a second, and we end up with 14.137. The last thing I want to do is go ahead and find if those equations, or if that figure is an equilateral triangle. So if it's an equilateral triangle, what's going to be different there? Oh, I need to plug in my phone. There we go. So if we have an equilateral triangle, well, now I'm going to create triangles on the top of these figures. That's kind of getting to be a messy little figure there. So if I create that again, here's my lines, kind of my perpendicular to the x-axis, and I'm going to create triangles on the top of it that are equilateral triangles. So again, I'm going to have a small triangle, working my way up to a big triangle, going back down to a small triangle. Again, you can play with that animation to see what those equilateral triangles are going to look like. So what's the area of an equilateral triangle? Well, from our note cards, we have radical 3 over 4 side squared dx. So our side is going to simply be, again, that function. So I'm integrating from negative 3 to 3 of the square root of 3 over 4. My side, which in this case is going to be that function, the square root of 9 minus x squared dx. Going ahead and simplifying this a little bit. Again, oh, that's a 4. Take that radical 3 over 4 out of my radical, or out of my integration, because it's a constant. So I integrate from negative 3 to 3 of 9 minus x squared dx. So in my calculator, I'm going to go ahead and integrate from negative 3 to 3 of that 9 minus x squared dx. I know I didn't put in that radical 3 over 4. You can at this point in time if you want. I'm going to go ahead and find that value. I'm going to divide it by 4, and that's going to give me 9. So I'm going to have 9 radical 3 as my exact answer. And if I take 9 and multiply it by radical 3, I can get the approximate answer of 15.588. And that gives me an approximate volume of that figure. And this allows us now to be able to find the volume of a known cross-section.